Tonight, we're going to explore something that most people never think about. When scientists talk about the observable universe, they're talking about a region of space that's roughly 93 billion light-years across. But here's the thing that should make you pause. Just because we call it observable doesn't mean we've actually observed it, not even close. By the end of this journey, you're going to understand exactly how much we've missed and why most of the universe remains invisible to us. Before we go any further, if you find this exploration interesting, a quick like or subscribe really helps the channel grow. Now, let's dive in. When you look up at the night sky on a clear evening away from city lights, how many stars do you think you can see? With perfect conditions and perfect eyesight, the human eye can see about 9,000 individual stars across the entire sky. Our galaxy alone contains somewhere between 100 billion and 400 billion stars. You're seeing roughly 0.00002% of just our own galaxy's stars. Now, extend that thought. There are approximately 2 trillion galaxies in the observable universe, each containing billions or even trillions of stars. The total number of stars has been estimated at around 200 billion trillion, and we can see 9,000 of them with our eyes. This gives you a sense of the scale we're dealing with. But it gets more interesting when we talk about galaxies specifically. While individual stars are too numerous to count, galaxies are the basic structures of the universe. They're the cities of stars, the building blocks of cosmic architecture. Here's where things get strange. We know there are about 2 trillion galaxies out there based on careful observations and mathematical projections. But the number we've actually observed in detail, as of 2025, the most comprehensive galaxy surveys have catalogued somewhere between 10 million and 50 million galaxies. Let's be generous and say 50 million. That's about 0.0025% of all galaxies. Put another way, for every galaxy we've observed in detail, there are roughly 40,000 we haven't looked at yet. If the universe were a library with 1 million books, we've read about 25 of them. And we're trying to understand the entire story based on those 25 books. Now, you might wonder why this is the case. We have powerful telescopes. We've been studying astronomy for centuries. The answer comes down to a combination of factors: time, technology, and the sheer scale of the task. Consider the size of the sky. The entire celestial sphere covers about 41,000 square degrees. The most powerful telescopes, like Hubble or James Webb, don't look at the whole sky at once. They look at tiny patches. The famous Hubble Ultra Deep Field shows about 10,000 galaxies in an area covering about 1/13 millionth of the entire sky. If the entire sky were the size of the United States, the Hubble Ultra Deep Field would be about the size of a tennis court. And it took Hubble hundreds of hours of exposure time to capture that single image. This is the fundamental problem. To see faint, distant galaxies, you need to stare at one spot for a long time. But the sky is enormous. There are millions of these patches, and we can only look at them one at a time. Second, there's the issue of technology and resolution. Not all observations are created equal. You can detect a galaxy, meaning you can see that something is there, a faint smudge of light in your image. But detecting it and observing it in detail are very different things. Detection might tell you a galaxy exists and roughly where it is. But to really understand that galaxy, to know its distance, its composition, its age, its structure, you need spectroscopy. You need to split its light into component wavelengths and analyze the patterns. And spectroscopy takes time. A lot of time. The Sloan Digital Sky Survey, which ran for years and produced one of the most comprehensive maps of galaxies ever made, obtained spectra for about 2 million galaxies. 2 million sounds impressive until you remember there are 2 trillion galaxies total. That's 0.1%. 0.1% of all galaxies have been analyzed spectroscopically. Most of what we count as observed galaxies are photometric detections, broad imaging, where we can see that something is there and maybe measure how bright it is and what color it appears, but we don't have detailed information. Think of it like this. Imagine you're trying to understand all the cities on Earth. Photometric detection is like flying over a city at night and seeing lights. You know there's a city there. You can estimate roughly how big it is based on how much light you see. But you don't know what the buildings look like, what language people speak, what the culture is, what industries drive the economy. For that, you need to land, walk around, talk to people, study the place in detail. That's spectroscopy. And we've only done the equivalent of detailed ground visits to about 2 million cities out of 2 trillion. The rest are just lights seen from an airplane. Third, there's the issue of distance and faintness. The universe is expanding. Light from distant galaxies gets stretched as it travels, a phenomenon called redshift. The farther away a galaxy is, the more its light is redshifted into longer wavelengths. Very distant galaxies have their light shifted so far into the infrared that optical telescopes can't see them at all. You need infrared telescopes like James Webb, and even then, the light is incredibly faint, reduced to just a handful of photons. Detecting them requires long exposure times and extremely sensitive instruments. Now, let's talk about what we mean when we say observable universe. This term confuses people because it sounds like we're talking about what we've observed, but that's not what it means. The observable universe is the region of space from which light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old. Light travels at 300,000 kilometers or 186,000 miles per second. So light from very distant regions hasn't reached us yet. Here's where it gets tricky. The universe has been expanding while that light was traveling. When you account for expansion, the edge of the observable universe is about 46.5 billion light-years away in every direction, making the observable universe about 93 billion light-years across. Everything within this sphere is potentially observable. The light exists. We could, in theory, build telescopes powerful enough to see all of it, but we haven't. Most of the observable universe remains unobserved. The light is passing by Earth right now, but we haven't captured it yet. This is what I mean by the invisible universe. It's not a mysterious dark realm beyond our ability to see. It's simply the part we haven't looked at yet. Let me give you a specific example. In 2025, astronomers using James Webb announced the discovery of over 1,700 groups of small galaxies in the early universe, less than 1 billion years after the Big Bang. They're incredibly far away and faint. Before Webb, we didn't know these galaxies existed. The light from these galaxies has been traveling for over 13 billion years. It passed by Earth countless times, while humans evolved and built civilizations. But we didn't see it because we didn't have sensitive enough infrared telescopes pointed in the right direction. This discovery revealed something surprising. These small galaxies appear to have played a major role in reionizing the universe, a crucial phase when the first stars formed and their radiation ionized the hydrogen gas filling space. Before this, astronomers thought larger galaxies were responsible. But Webb's observations suggest small, faint galaxies might have been the main drivers. This shows that what we haven't seen isn't just more of the same. It contains surprises that challenge our understanding. Let's talk briefly about how we got here. In the early 1900s, we didn't even know galaxies existed beyond our own. Astronomers saw fuzzy patches called nebulae, but didn't know what they were. In 1920, there was a famous debate about whether these spiral nebulae were small objects within the Milky Way or distant island universes. Then in 1923, Edwin Hubble resolved individual stars in the Andromeda Nebula and measured its distance at about 900,000 light-years. This proved Andromeda was a separate galaxy. Suddenly, the universe got much bigger. By the 1950s, photographic surveys had catalogued thousands of galaxies. The 1990s brought the digital revolution with CCD cameras, far more sensitive than film. The Sloan Digital Sky Survey obtained spectra for about 2 million galaxies by 2025, providing detailed information about distances and properties. But SDSS only covered about 1/3 of the sky, and its depth was limited. Hubble Space Telescope, launched in 1990, revolutionized our view with deep field images revealing thousands of faint galaxies. Based on Hubble observations, astronomers initially estimated 100 billion to 200 billion galaxies. Then, in 2016, using mathematical modeling, they revised the estimate to about 2 trillion galaxies. That's 10 times more than previously thought. Why? Because Hubble couldn't see the faintest, most distant galaxies. When astronomers accounted for these statistically, they realized the universe contained far more galaxies than we'd observed. Enter James Webb Space Telescope. Webb launched in December 2021 and is an infrared telescope designed to see light that Hubble can't detect. With a mirror 6.5 meters, or about 21 feet across compared to Hubble's 2.4 meter or almost 8-foot mirror, Webb is much more sensitive. In its first few years, Webb has found galaxies from just a few 100 million years after the Big Bang, challenging our models of galaxy formation. In 2024 and early 2025, the Euclid space mission started releasing its data. Euclid is designed to map billions of galaxies across a large portion of sky. In its first year, it catalogued 26 million galaxies in deep field observations. As Euclid continues, it will observe billions of galaxies, but even billions is still a small fraction of 2 trillion. We've made incredible progress, but we've still only scratched the surface. One reason is telescope time. There are only a handful of world-class telescopes capable of observing faint, distant galaxies. They're in constant demand with fierce competition for observing time. There simply aren't enough telescopes and hours in the year to observe everything. Another challenge is observing faint objects. Galaxies far away appear incredibly faint. Their light spreads out over an ever-increasing sphere. By the time it reaches us, a distant galaxy might emit just a few photons per second, hitting our telescope. To detect such faint objects requires long exposure times, dark skies free from light pollution, minimal moonlight, and perfect atmospheric conditions. There's also cosmic dust. Dust in our Milky Way blocks light from distant objects. About 10 to 20% of the sky is obscured by the Milky Way's disk, a region called the zone of avoidance. We can't see distant galaxies through it at optical wavelengths. That means about 10 to 20% of the universe is hidden by dust in our own galaxy. Let's talk about what kinds of galaxies make up the invisible universe. You might think they're just copies of galaxies we've already seen, but that's not true. There's a bias in our observations. We tend to see the brightest, largest, most massive galaxies because they're easiest to detect. A giant elliptical galaxy with 1 trillion stars is much easier to spot than a dwarf galaxy with only a few 100 million stars. But dwarf galaxies are actually far more common. Most galaxies in the universe are small. We know this from studying nearby galaxies in our local neighborhood. In the local group, which includes the Milky Way, Andromeda, and about 80 smaller galaxies, most members are dwarf galaxies. If this ratio holds across the universe, then the vast majority of 2 trillion galaxies are small, faint dwarfs that are very hard to detect at large distances. Dwarf galaxies matter because they're the building blocks that merge to form larger galaxies. They contain clues about dark matter. They might host unusual types of stars or black holes. The Milky Way itself is constantly consuming dwarf galaxies. The Sagittarius Dwarf Elliptical Galaxy is being torn apart by our gravity right now, its stars streaming out into long trails. The Magellanic Clouds, visible from the southern hemisphere, are also being disrupted and will likely merge with the Milky Way in the future. There's a special class called ultra-faint dwarf galaxies that are even more extreme. These tiny satellites contain only a few thousand stars compared to the Milky Way's 100 billion. Some are so dim that the entire galaxy is fainter than a single bright star. We know of about 60 ultra-faint dwarfs in our local group, but theoretical models suggest there should be hundreds or thousands orbiting the Milky Way alone. And that's just in our neighborhood. Across the universe, there are probably trillions of these ultra-faint dwarfs, contributing to the galaxy count, but remaining undetected because they're too dim. There's also the question of entirely new structures. In 2024, astronomers announced the discovery of the Big Ring, a massive circular arrangement of galaxies about 1.3 billion light-years across. According to our understanding of cosmology, the universe should be relatively uniform on very large scales. There shouldn't be structures this big. Yet there it is, along with the giant arc, another huge structure. These were invisible until recently, not because we couldn't see the individual galaxies, but because we hadn't mapped enough to see the pattern. Let's think about the future. What will it take to make more of the invisible universe visible? The answer is more powerful telescopes and better technology. The Nancy Grace Roman Space Telescope will launch in the late 2020s with a field of view 100 times larger than Hubble's. Roman will observe hundreds of millions of galaxies across thousands of square degrees, giving us a much better sense of cosmic structure. On the ground, the extremely large telescope is being built in Chile with a mirror 39 meters or 128 feet across, making it the largest optical telescope in the world. The ELT will see fainter objects in greater detail than any current telescope. The square-kilometer array being built in Australia and South Africa will be the most sensitive radio telescope ever constructed. It will map neutral hydrogen gas in galaxies, revealing invisible reservoirs of gas from which future stars will form. But even with all these telescopes working together, we'll still observe only a small fraction of 2 trillion galaxies. We might go from 0.0025% to 1 or 2%. The fundamental problem is time. There are only so many hours in a day and nights in a year. Let me tell you about some specific observation challenges that contribute to what remains invisible. When astronomers observe the sky, they're fighting numerous sources of noise and interference. Light pollution from cities brightens the sky. Atmospheric turbulence blurs images. The moon, when bright, washes out faint objects. Even dust and gas in our solar system creates a faint glow. Even in space above Earth's atmosphere, challenges remain. Cosmic rays constantly bombard detectors, creating false signals. The instruments generate noise. Detectors have a dark current, a small signal, even when no light hits them. Every photon from a distant galaxy must be distinguished from all these noise sources. For very faint objects, the signal might be only slightly larger than noise. You need long integration times, exposing the detector for hours or days. The Hubble Ultra Deep Field required over 11 days of total exposure time across hundreds of orbits. To observe the whole sky to this depth would require about 300,000 years with a single telescope. There's also the challenge of identifying what you're seeing. A deep image might capture thousands of faint objects. Most are galaxies, but some are stars, some are asteroids, some are artifacts. You need to distinguish them. Galaxies appear as extended fuzzy blobs, while stars appear as points. But very distant galaxies can also appear as points. You need multiple observations to identify asteroids which move. You need spectroscopy to confirm objects. For every detected object, hours of analysis might be required for proper classification. Even with machine learning, there's a processing speed limit. Millions of galaxies sit in existing data archives that haven't been thoroughly analyzed because there aren't enough astronomers to process everything. Selection effects systematically bias our view. Bright objects are easier to find than faint ones. Large objects are easier to resolve than small ones. Objects with certain colors stand out more. These biases mean the galaxies we've observed aren't representative. They're skewed toward bright, large, colorful galaxies in well-studied regions. Astronomers correct for selection effects using statistical methods, modeling the probability of detecting objects based on their properties. This is how we arrive at 2 trillion galaxies, even though we've only observed 50 million. The estimate is based on observations plus statistical corrections. But these corrections have uncertainties. This raises a philosophical question. If we can never observe most of the universe, does it matter? Is there value in knowing that 99.9% of galaxies are out there even if we can't study them individually? I think there is. Understanding the limits of our knowledge keeps us humble. It reminds us the universe is far larger and more complex than we can fully comprehend, and it drives us to keep exploring. There's also the practical consideration that what we haven't seen might contain things we need to know about. Suppose there's a common type of galaxy we've never observed because it's faint or in unobserved sky regions. Our models are built on what we've seen. If we're missing a major component, our models might be wrong. This has happened before. Dark matter was discovered because galaxy motions didn't match expectations. We had to invent dark matter to explain observations. What if there are other invisible components we're missing? Let me bring this to a human scale. Why should you care about the invisible universe? You're not an astronomer. What does it matter that we've only observed a tiny fraction of galaxies? I think it matters because it changes your perspective. We live in an age where information seems abundant. It's easy to feel like we know a lot, like we've figured most things out. The invisible universe reminds us that we haven't. The universe is vastly larger and more complex than our everyday experience suggests. Most of what exists is beyond our current ability to study. This should inspire wonder and humility. Wonder at the sheer scale of the cosmos. Humility at how little we actually know despite all our progress. It also has practical implications for thinking about life in the universe. If we've only observed 0.0025% of galaxies, we've barely begun searching for signs of life. Every galaxy contains billions of stars. Every star might have planets. The number of potentially habitable worlds is staggering. If life is even moderately common, the universe should be teeming with it. But we've looked at such a tiny fraction that our failure to find signs doesn't mean much. The invisible universe almost certainly contains life, perhaps even intelligent civilizations. We just haven't found them yet, because we haven't looked in enough places. This should make us more optimistic about the search for extraterrestrial intelligence. We're not running out of places to look, we're just getting started. The invisible universe contains trillions of galaxies we haven't examined. Each could host billions of habitable worlds. The odds that we're alone seem vanishingly small when you think about the scale involved. So what have we learned? The observable universe contains about 2 trillion galaxies, but we've only observed in detail a tiny fraction. We've learned about different types of objects that make up the invisible universe. We've learned about observation challenges, the time and resources required to detect faint, distant objects. And we've thought about the philosophical and practical implications of living in a universe where most of what exists remains unseen. The invisible universe is vast, far larger than the observed universe. For every galaxy we've studied, there are tens of thousands we haven't. For every star we've catalogued, there are trillions we haven't. This should fill us with wonder and humility. Wonder at the sheer scale, humility at the limits of our knowledge. But it should also inspire us to keep exploring. The invisible universe is not forever invisible. It's simply unseen so far. With better telescopes, more observing time, improved techniques, and continued dedication, we can make more of it visible. We'll never see it all, but we can see more. We can push the boundaries further. We can reveal new corners of the cosmos. Thank you for joining me on this journey through the invisible universe. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep dives into the cosmos. Remember, the universe is far larger than what we can see. Every time we look, we find something new. And that's the beauty of it. The invisible universe isn't empty. It's full of wonders we haven't discovered yet. It's full of galaxies waiting to be catalogued, stars waiting to be studied, and perhaps even civilizations waiting to be contacted. The frontier of cosmic exploration stretches endlessly before us. We're surrounded by mysteries, and that makes this the most exciting time to be alive and looking up at the stars. Good night, and may you never look at the night sky the same way again. Let's talk about the cosmic horizon, the ultimate limit on what we can see. Even with perfect telescopes and unlimited time, there are regions of the universe we can never observe. This isn't a technological limitation. It's a fundamental consequence of the expanding universe and the finite speed of light. Light from very distant regions of the universe is traveling toward us, but the universe is expanding faster than the light can close the gap. These regions are receding from us faster than the speed of light. Not because they're moving through space faster than light, which would violate the laws of physics, but because space itself is expanding between us and them. The expansion of space can carry objects apart faster than light can travel through space. This means there's a cosmic horizon beyond which we can never see. Light from regions beyond this horizon will never reach us. Ever. No matter how long we wait, no matter how powerful our telescopes become. Those regions are fundamentally invisible, cut off from us by the expansion of space. The exact location of this horizon depends on the details of the universe's expansion, which is driven by dark energy. Current estimates suggest that the cosmic horizon is about 46.5 billion light-years away. Everything beyond that is forever beyond our view. But here's the strange thing. The universe as a whole is probably much larger than the observable universe. It might even be infinite. If the universe is infinite, then the observable universe, the part we can see or could ever see, is an infinitesimal fraction of the whole. The invisible universe isn't just big. It's infinitely big. Let me try to make this concept clearer with an analogy. Imagine you're standing in the middle of a vast ocean. There's fog all around you, and you can only see about 1 kilometer or 6/10 of a mile in every direction. That visible circle, 2 kilometers or 1.2 miles across, is your observable ocean. Beyond the fog, the ocean continues. It might go on for thousands of kilometers or millions of miles. It might even be infinite. But you can't see it. You're limited by the fog. Now, imagine the fog is slowly receding, expanding outward. Every hour, you can see a little bit farther. But here's the twist. The ocean is also expanding. New water is being added everywhere, including beyond your visible horizon. And the ocean is expanding faster than the fog is receding. So even though your visible area is growing, there's always more ocean beyond your sight. In fact, the ocean beyond your horizon is growing faster than your horizon is expanding. That's the universe we live in. We can see farther every year as light from more distant regions reaches us. But the universe is expanding faster than light can travel, so there will always be regions beyond our horizon. This has profound implications. It means we're fundamentally isolated in the universe. There are galaxies and cosmic structures out there that we can never see, never study, never communicate with. They might as well be in a different universe for all the interaction we can have with them. This isolation isn't temporary, it's permanent. The cosmic horizon is a fundamental boundary, and it's getting worse. Dark energy is causing the expansion of the universe to accelerate. Galaxies that are currently just within our observable universe will eventually cross the horizon and disappear from view. In the far future, billions of years from now, the observable universe will contain fewer galaxies than it does today, because distant galaxies will have been carried beyond the cosmic horizon by the accelerating expansion. Future astronomers, if they exist, will look out and see a lonelier universe than we see today. But let's bring this back to the present. Right now, in 2025, we're living in a golden age of astronomy. We have more powerful telescopes than ever before. We have access to huge datasets, observations across the entire electromagnetic spectrum from radio waves to gamma rays. We have computer models that can simulate the evolution of the universe in incredible detail. And we have a community of thousands of astronomers around the world working to understand the cosmos. Despite all this progress, the invisible universe remains vast. We've observed a tiny fraction of the galaxies out there. Most of the universe is still unseen, still waiting to be discovered. Let me give you a sense of what we're missing by talking about some specific examples. Dwarf galaxies, as I mentioned, are probably the most common type of galaxy in the universe. But they're very hard to detect at large distances because they're faint. In our local group, we know of about 80 galaxies, and most of them are dwarfs. But we keep finding new ones. As recently as 2020, astronomers discovered new dwarf galaxies orbiting the Milky Way. These are galaxies in our own cosmic neighborhood, closer than Andromeda, and we're still finding new ones because they're so faint. If we're still discovering galaxies this close to home, imagine how many we're missing at cosmological distances, billions of light years away. The invisible universe is probably teeming with dwarf galaxies. Then there are ultra-diffuse galaxies. These are galaxies that are as large as the Milky Way in terms of diameter, but contain far fewer stars. They're spread out and faint, making them very hard to detect. We've only known about ultra-diffuse galaxies for about a decade. The first ones were discovered in the Coma cluster in 2015. Since then, we've found hundreds of them, but there are probably millions or billions in the universe. They're part of the invisible universe simply because they're so diffuse and faint that they're hard to see, even with good telescopes. There are also galaxies in voids. The universe has a large-scale structure, often described as a cosmic web. Galaxies are not uniformly distributed through space. Instead, they're concentrated in filaments and clusters, with vast, empty regions called voids in between. These voids can be hundreds of millions of light-years across. They're not completely empty. There are galaxies in voids, but they're rare and isolated. And because they're in regions of space we don't often survey, many of them remain undiscovered. The invisible universe includes these lonely galaxies drifting through the voids. And then there are galaxies obscured by dust, either dust in our own galaxy or dust in other galaxies between us and them. The zone of avoidance, the region of sky blocked by the Milky Way's disk, contains an estimated 100 million galaxies that we can't observe at optical wavelengths. We can detect some of them at infrared or radio wavelengths, but many remain invisible. Similarly, if there's a dusty galaxy between us and a more distant galaxy, the foreground galaxy can block our view, hiding the background galaxy. This is called obscuration, and it's responsible for some of the invisible universe. Let's talk about the observable universe's expansion and how it affects what we can see. I mentioned earlier that the observable universe is about 93 billion light-years across, even though the universe is only 13.8 billion years old. This seems like a contradiction. How can we see light from objects that are 93 billion light-years away if light has only been traveling for 13.8 billion years? The answer is that space has been expanding while the light was traveling. When light left a distant galaxy 13 billion years ago, that galaxy was much closer to us, maybe only a few billion light-years away. But while the light was traveling toward us, space expanded, carrying the galaxy farther away. By the time the light reaches us, the galaxy is now about 46 billion light-years away. And since space is symmetrical, there are galaxies equally far in the opposite direction, making the observable universe 93 billion light-years across. This expansion has another effect. It stretches the light as it travels. This is redshift, light from a galaxy that's moving away from us due to the expansion of space gets stretched to longer wavelengths. Visible light might get stretched into the infrared. Ultraviolet light might get stretched into the visible. The farther away a galaxy is, the faster it's receding, and the more its light is redshifted. For the most distant galaxies, the ones we see with the James Webb Space Telescope, the redshift is extreme. Light that was emitted as ultraviolet is now arriving as deep infrared. This is why infrared telescopes like Webb are so important for studying the early universe. The galaxies are so far away and receding so fast that their light is shifted out of the visible range entirely. But redshift does more than change the wavelength of light. It also makes galaxies fainter. The energy of light is related to its wavelength. When light is redshifted, its energy decreases. So a photon that left a galaxy as high-energy ultraviolet light arrives at Earth as low-energy infrared light. This means distant galaxies appear dimmer than they would if the universe weren't expanding. Combined with the normal dimming due to distance, this makes very distant galaxies incredibly faint. They're emitting plenty of light, but by the time it reaches us, it's been redshifted and dimmed so much that detecting it requires the most sensitive instruments we have. This is another reason why so much of the universe remains invisible. The galaxies are out there, shining brightly in their local reference frame. But their light is so redshifted and dimmed by the time it gets to us that we can barely detect it. There's also the question of cosmic variance. When we observe a small patch of sky, we're seeing a snapshot of that particular region. But the universe isn't perfectly uniform. Some regions have more galaxies than others. Some regions have different types of galaxies. If we only observe a small area, we might get an unrepresentative sample. Imagine trying to understand Earth's geography by looking at a single square kilometer, or about 4/10 of a square mile. If that square happened to be in the middle of the ocean, you'd conclude Earth is mostly water with no land. If it happened to be in the middle of a desert, you'd conclude Earth is dry and barren. To get an accurate picture, you need to sample many different locations. The same is true for the universe. To understand the full diversity of galaxies and cosmic structures, we need to observe large volumes of space. But the deeper we look, the farther back in time we see, and the smaller the volume we can survey in detail. This is a fundamental trade-off. We can look deep, or we can look wide, but it's hard to do both. The Hubble Ultra Deep Field, for example, looked incredibly deep, seeing galaxies from when the universe was very young, but it only covered a tiny area of sky. The Sloan Digital Sky Survey covered a large area, about 1/3 of the sky, but it didn't look as deep. It missed faint, distant galaxies. Ideally, we'd like to survey the entire sky at the depth of the Hubble Ultra Deep Field. But with current technology, that would take thousands of years, so we're forced to make choices. We can study a few regions in great detail, or we can survey large areas more shallowly. Both approaches are valuable, but both leave parts of the invisible universe unseen. Let me tell you about a recent discovery that illustrates how much we're missing. In 2023, astronomers announced the discovery of a massive galaxy cluster called El Gordo, Spanish for the Fat One. This cluster is about 7 billion light-years away and contains thousands of galaxies. It's one of the most massive clusters ever found. But here's the interesting part. El Gordo was discovered not by a deep optical survey, but by its effect on the cosmic microwave background, the faint radiation left over from the Big Bang. The hot gas in the cluster scatters the microwave background radiation, creating a subtle signal that can be detected. Astronomers found this signal and then used optical telescopes to confirm the cluster. This discovery technique, called the Sunyaev-Zeldovich effect, can find massive galaxy clusters that might be missed by optical surveys. It's another tool for revealing the invisible universe, and it shows that different wavelengths and different techniques can uncover structures we didn't know about. There's also the question of time. The universe has been around for 13.8 billion years. When we look at distant galaxies, we're seeing them as they were billions of years ago. The light from a galaxy, 10 billion light-years away, shows us what that galaxy looked like 10 billion years ago. That galaxy has continued to evolve. It might look completely different now. Stars have formed and died. It might have merged with other galaxies. It might have changed from a spiral to an elliptical. But we can't see any of that because the light showing us the galaxy's current state won't reach Earth for another 10 billion years. In a sense, the present state of the distant universe is invisible to us. we can only see the past. The invisible universe includes not just galaxies we haven't observed, but also the current state of galaxies we have observed. This creates an interesting situation. When we make a map of the universe, showing where all the galaxies are, we're not making a map of the universe as it is now. We're making a map of the universe as it was at different times in the past. A galaxy 1 billion light-years away is shown as it was 1 billion years ago. A galaxy 10 billion light-years away is shown as it was 10 billion years ago. It's like making a family photo album where each person's picture is from a different year. Your photo is from this year. Your siblings is from 5 years ago. Your parents are from 20 years ago. Your grandparents are from 50 years ago. The album doesn't show the family as it is now. It shows a composite of different times. That's what our maps of the universe are. They're composites of the universe at different epochs. The true present state of the entire universe is fundamentally invisible to us because light hasn't had time to bring us that information yet. Let's talk about the role of dark matter and dark energy in the invisible universe. When astronomers talk about what we can't see in the universe, they often mean dark matter and dark energy. These are components of the universe that don't emit light. We can't see them directly. We only know they exist because of their gravitational effects. Dark matter makes up about 27% of the universe's total energy density. Normal matter, the stuff that makes up stars, planets, and us, is only about 5%. Dark matter doesn't interact with light. It doesn't emit it, absorb it, or reflect it. It's invisible to all our telescopes. But we know it's there because galaxies and galaxy clusters have more mass than we can account for with visible matter alone. The extra mass is dark matter. Dark energy is even stranger. It makes up about 68% of the universe's total energy density. It's a mysterious force that's causing the expansion of the universe to accelerate. We don't know what dark energy is. We can't see it or detect it directly. We only know it exists because the universe is expanding faster than it should be based on the matter we can account for. So, in a very real sense, 95% of the universe is invisible. Not invisible in the sense that we haven't observed it yet, but invisible because it doesn't emit light and we don't have any way to detect it directly. This is a different kind of invisible universe. It's not galaxies we haven't looked at yet. It's components of the universe that are fundamentally different from normal matter, and that might be impossible to observe directly. But for the purposes of this discussion, I'm focusing on the galaxies we haven't observed yet. The normal matter component of the universe that emits light, but that we simply haven't looked at. Even within the 5% of the universe, that's normal matter. We've only observed a tiny fraction. If you think about it, this makes the invisible universe even larger. Not only have we observed less than 1% of the galaxies in the observable universe, but those galaxies only represent about 5% of the universe's total content. The rest is dark matter and dark energy, completely invisible to our telescopes. The universe is far more invisible than most people realize. Now, let's think about what all this means for the search for extraterrestrial life. If there are 2 trillion galaxies in the observable universe, and we've only looked at a few million of them in any detail, what are the chances we found all the life out there? Pretty slim, right? Every galaxy contains billions of stars. Many of those stars have planets. Based on observations from missions like Kepler and TESS, we know that planets are common. Most stars have at least one planet, some have many. If even a tiny fraction of those planets are habitable, And if life can arise on habitable planets, the universe should be teeming with life. But we've only searched for signs of life on a handful of planets. We've looked for radio signals from nearby stars, but we've only monitored a tiny fraction of the sky, and for a limited time. The search for extraterrestrial intelligence, or SETI, is like trying to have a phone conversation with someone when you don't know their number, you don't know what language they speak, and you're only listening to one frequency out of billions. The invisible universe almost certainly contains life. Statistically, it would be astonishing if Earth were the only planet with life, but finding that life is incredibly difficult. The universe is vast. Signals from alien civilizations would be faint by the time they reach us. And we don't know what to look for. Are they using radio, lasers, some form of communication we haven't thought of? The invisible universe might be full of alien civilizations, but they're invisible to us because we haven't looked in the right places or at the right wavelengths or for long enough. This is one of the most exciting aspects of exploring the invisible universe. Every new galaxy we observe, every new planet we study, increases the chances that we might find signs of life. Let's talk about citizen science and how ordinary people can help explore the invisible universe. Professional astronomers can't analyze all the data being collected by telescopes. There's simply too much of it. This is where citizen scientists come in. Projects like Galaxy Zoo allow people to classify galaxies by looking at images online. You don't need any special training. The website shows you an image of a galaxy and asks you simple questions. Is it spiral or elliptical? Is it smooth or does it have features? Your classifications are combined with those of thousands of other people, and the results are used by astronomers to understand galaxy populations. Galaxy Zoo has classified millions of galaxies, far more than professional astronomers could have done alone. It's a way for anyone to contribute to revealing the invisible universe. Another project, Planet Hunters, asks people to look at data from the Kepler and TESS missions and identify dips in starlight that might indicate a planet passing in front of its star. Citizen scientists have discovered dozens of exoplanets this way, some of which were missed by automated algorithms. There are similar projects for finding asteroids, classifying supernovae, mapping the moon, and more. These projects show that exploring the universe isn't just for professionals. Anyone with an internet connection can participate. And in doing so, you're helping to make the invisible universe a little less invisible. Let me give you a sense of the scale we're dealing with by talking about the cosmic web. On the largest scales, the universe has a structure that looks like a three-dimensional spider web. Galaxies are concentrated along filaments, thin strands of matter that stretch across hundreds of millions of light years. Where filaments intersect, you get dense clusters of thousands of galaxies. Between the filaments are voids, vast empty regions with very few galaxies. This cosmic web is the result of gravity acting on tiny density fluctuations in the early universe. Regions that were slightly denser attracted more matter, growing over billions of years into the filaments and clusters we see today. But here's the thing. We've only mapped the cosmic web in small regions of the universe. Most of the web is invisible to us because we haven't observed enough galaxies to see the full structure. Imagine trying to understand a spider web by looking at a few tiny patches. You might see a strand here, a junction there, but you wouldn't see the overall pattern. That's where we are with the cosmic web. We've mapped parts of it, and we can use computer simulations to predict what it should look like based on our theories of gravity and dark matter. But actually observing it requires mapping millions of galaxies across large volumes of space. The invisible universe contains the full extent of the cosmic web, the complete large-scale structure of the universe. We won't see it all until we've observed far more galaxies than we have so far. Let's talk about some of the challenges of observing the early universe. The James Webb Space Telescope was designed specifically to study the first galaxies that formed after the Big Bang. These galaxies are incredibly far away, which means their light has been traveling for over 13 billion years. By the time it reaches us, it's been redshifted into the infrared. Webb can see this infrared light, but there are challenges. The galaxies are incredibly faint. They're small, containing far fewer stars than modern galaxies. And they're surrounded by neutral hydrogen gas that absorbs ultraviolet light. This makes them even harder to detect. Webb has found hundreds of these early galaxies, and they're surprising. Some are larger and brighter than expected. Some formed stars at incredible rates. They're challenging our understanding of how galaxies form and evolve. But even Webb can only see the brightest of these early galaxies. There are probably millions or billions of faint early galaxies that are below Webb's detection limit. They're part of the invisible universe, waiting for the next generation of telescopes to reveal them. One of the most exciting aspects of modern astronomy is the discovery of transient events, things that change or appear suddenly. Supernovae, stars exploding at the end of their lives, can briefly outshine entire galaxies. Gamma-ray bursts, the most energetic explosions in the universe, can release more energy in a few seconds than the sun will emit in its entire lifetime. Tidal disruption events, where a star gets too close to a black hole and is torn apart, create bright flares that last for months. These events are happening all the time throughout the universe, but we only see the ones that happen to occur in regions we're monitoring. The invisible universe contains countless transient events that we never observe because we're not looking in the right place at the right time. There's a project called the Zwicky Transient Facility that surveys the northern sky every few nights looking for transient events. It's found thousands of supernovae, asteroids, and other changing objects, but it can only survey the relatively nearby universe. Transient events in distant galaxies are too faint for most surveys to detect. The invisible universe is full of explosions and eruptions we never see. Every night, thousands of stars explode in galaxies, billions of light years away. Most of those explosions go unnoticed. They happen, they fade, and no one on Earth knows about them. They're part of the invisible universe. Let me try to put all this into perspective with a final thought. The observable universe contains everything we could possibly see. It's the full extent of space from which light has had time to reach us. Within this observable universe, there are about 2 trillion galaxies. But we've only observed in detail a tiny fraction of them. Maybe 50 million out of 2 trillion. That's 0.0025%. For every galaxy we've studied, there are 40,000 we haven't looked at. And those are just the galaxies we know exist. There might be types of structures or objects we haven't discovered yet because we haven't observed enough of the universe to find them. The invisible universe is vast beyond comprehension. It's not a distant, unreachable realm. It's all around us, filling the sky in every direction. The light from invisible galaxies is passing by Earth right now, traveling through space towards some distant observer who might see what we've missed. In the coming decades, new telescopes and surveys will reveal more of the invisible universe. The Roman Space Telescope will survey billions of galaxies. The extremely large telescope will see fainter and more distant objects than ever before. The square kilometer array will map the universe at radio wavelengths. AI and machine learning will help us analyze the mountains of data these instruments will produce. We'll go from having observed 0.0025% of galaxies to maybe 1% or even a few percent. That's progress. But even at a few percent, 95% or more of the universe will still be invisible. We'll still be scratching the surface. And that's okay. The invisible universe isn't a failure. It's a challenge. It's an invitation. It's a reminder that the universe is far larger and more complex than we can fully comprehend. Every galaxy we observe, every star we study, every planet we discover adds to our knowledge. We're building a picture of the universe one observation at a time. It's a picture that will never be complete, but it's getting richer and more detailed with every passing year. The invisible universe will always be there, beckoning us, challenging us to look deeper, to build better instruments, to ask better questions. So the next time you look up at the night sky and see a few thousand stars, remember what you're not seeing. You're not seeing the 100 billion other stars in our galaxy. You're not seeing the 2 trillion galaxies beyond our own. You're not seeing the cosmic web, the large-scale structure that organizes the universe. You're not seeing the dwarf galaxies, the ultra-diffuse galaxies, the galaxies in voids, the galaxies hidden by dust. You're not seeing the supernova explosions happening right now in distant galaxies. You're not seeing the planets orbiting other stars. You're not seeing the alien civilizations that might be out there. All of that is invisible to your eyes, but it's there. The invisible universe surrounds us, waiting to be discovered. We've made incredible progress in the centuries since we first realized galaxies exist. We've mapped millions of them. We've measured the expansion of the universe. We've discovered dark matter and dark energy. We've found thousands of exoplanets. We've looked back to the early universe and seen galaxies forming when the cosmos was young, but we've only just begun. The invisible universe is vast. It contains mysteries we can't even imagine yet. And that's what makes astronomy exciting. There's always more to discover. Always another galaxy to observe. Always another question to answer. The universe is infinite in its ability to surprise us. And most of it is still invisible, waiting for the next generation of astronomers to reveal its secrets. Now, let's dive deeper into specific examples of what makes up the invisible universe. Understanding the details helps us appreciate just how much we're missing. I want to walk you through different categories of objects and structures that exist, but remain largely unobserved. Each category represents a vast population of cosmic objects that we know must be out there, but that we've barely begun to catalogue. First, let's talk about low-surface brightness galaxies. These are galaxies that are spread out and diffuse. They contain plenty of stars, sometimes as many as the Milky Way, but those stars are distributed over a much larger volume. This makes them extremely faint per unit area. Imagine 2 streetlights. One is a bright spotlight, concentrating its light into a small area. The other is a dim flood lamp, spreading the same total amount of light over a much larger area. From a distance, the spotlight is easy to see. The flood lamp is barely visible. Low-surface brightness galaxies are like cosmic flood lamps. They're there, emitting light, but spread so thinly that they're incredibly hard to detect. These galaxies were largely unknown until the 1980s. Astronomers had missed them for decades because standard survey techniques were optimized to find bright, compact objects. When someone finally looked specifically for diffuse galaxies, they found them everywhere. Today we know of thousands of low-surface brightness galaxies, but there are probably billions, in the observable universe. Most remain invisible simply because they're so faint. Standard galaxy surveys don't detect them unless they're very close to us. The invisible universe contains vast numbers of these ghostly galaxies, so diffuse they're almost transparent. There's a special class of ultra-faint dwarf galaxies that are even more extreme. These are tiny satellite galaxies, orbiting larger galaxies like the Milky Way and Andromeda. They contain only a few thousand stars, compared to the Milky Way's 100 billion or more. Some of these ultra-faint dwarfs are so dim that the entire galaxy is fainter than a single bright star. They're among the least luminous objects in the universe that we'd classify as galaxies. We know of about 60 ultra-faint dwarf galaxies in our local group, but theoretical models suggest there should be hundreds or even thousands of them orbiting the Milky Way alone. We haven't found them because they're so incredibly faint. You need deep observations with large telescopes to detect them, and that's just in our immediate neighborhood. In other galaxy groups and clusters across the universe, there are probably trillions of these ultra-faint dwarfs. They're part of the invisible universe, contributing to the total galaxy count, but remaining undetected because they're too dim. Let's talk about intergalactic stars, sometimes called intracluster stars. These are stars that don't belong to any galaxy. They're out in the space between galaxies, drifting alone or in loose groups. How do stars end up between galaxies? It happens during galaxy collisions and mergers. When two galaxies collide, the gravitational interactions can fling stars out at high speeds. Those stars escape their parent galaxies and drift into intergalactic space. In galaxy clusters, where hundreds or thousands of galaxies are gravitationally bound together, there can be huge populations of these orphan stars. Observations of nearby galaxy clusters suggest that between 10 and 40% of the total starlight comes from intracluster stars rather than from galaxies themselves. That's an enormous population of stars that's difficult to observe because they're not concentrated in galaxies. They're spread out over huge volumes of space, making them extremely faint. But theoretical models suggest there should be hundreds or even thousands of them orbiting the Milky Way alone. We haven't found them because they're so incredibly faint. You need deep observations with large telescopes to detect them, and that's just in our immediate neighborhood. In other galaxy groups and clusters across the universe, there are probably trillions of these ultra-faint dwarfs. They're part of the invisible universe, contributing to the total galaxy count, but remaining undetected because they're too dim. Let's talk about intergalactic stars, sometimes called intracluster stars. These are stars that don't belong to any galaxy. They're out in the space between galaxies, drifting alone or in loose groups. How do stars end up between galaxies? It happens during galaxy collisions and mergers. When two galaxies collide, the gravitational interactions can fling stars out at high speeds. Those stars escape their parent galaxies and drift into intergalactic space. In galaxy clusters, where hundreds or thousands of galaxies are gravitationally bound together, there can be huge populations of these orphan stars. Observations of nearby galaxy clusters suggest that between 10 and 40% of the total starlight comes from intracluster stars rather than from galaxies themselves. That's an enormous population of stars that's difficult to observe because they're not concentrated in galaxies. They're spread out over huge volumes of space, making them extremely faint. The invisible universe contains uncounted trillions of these wandering stars. They're out there, orbiting in the gravitational potential of galaxy clusters, but we can barely detect them even in nearby clusters. In distant clusters, they're completely invisible to current telescopes. This represents a significant fraction of the stars in the universe that we're not accounting for in our galaxy counts. When we count galaxies, we're missing the stars that have been expelled from galaxies. It's like trying to understand Earth's population by only counting people inside buildings and missing everyone who's outside. There's also the question of primordial galaxies, the very first galaxies that formed in the universe. The James Webb Space Telescope is designed to find these early galaxies, and it's had remarkable success. In its first couple of years, Webb has found galaxies from when the universe was only a few 100 million years old. These are among the earliest galaxies we've ever observed. But even Webb has limits. The smallest, faintest primordial galaxies are beyond its detection threshold. These tiny galaxies might have contained only a few million stars, enough to ionize the surrounding gas, but too faint for us to see directly. Theoretical models suggest there should be vast numbers of these small primordial galaxies. They might have been the seeds that merged together to form larger galaxies like the Milky Way. But most of them are invisible to us, too faint and too distant for current technology to detect. This matters because these invisible primordial galaxies played crucial roles in cosmic history. They were responsible for reionization, the process that transformed the universe from opaque to transparent by ionizing the hydrogen gas that filled space. Without understanding these tiny early galaxies, we can't fully understand how the universe evolved from the smooth, nearly uniform state after the Big Bang to the structured universe full of galaxies we see today. The invisible universe contains the full story of cosmic dawn, the era when the first stars and galaxies lit up. We're seeing glimpses of that story with Webb, but most of the details remain hidden. Let me tell you about galaxy groups and how they relate to the invisible universe. Most galaxies aren't isolated. They exist in groups or clusters held together by gravity. Our Milky Way is part of the local group, which includes Andromeda, Triangulum, and about 80 smaller galaxies. The local group spans about 10 million light-years, or roughly 6 million miles. It's our cosmic neighborhood. Beyond the local group, there are thousands of other galaxy groups and hundreds of large galaxy clusters. Each cluster might contain hundreds or thousands of galaxies. The Virgo cluster, the nearest large cluster to us, contains over 2,000 galaxies. The Coma cluster contains over 1,000. These are the biggest structures held together by gravity in the universe. But here's the thing. We've catalogued the galaxies in nearby clusters reasonably well. The Virgo cluster is only about 53 million light-years away, close enough that we can detect even relatively faint galaxies. But most galaxy clusters are much farther away. As you go to greater distances, you can only see the brightest cluster members. The faint dwarf galaxies that make up the majority of cluster populations become invisible. So our catalogues of distant galaxy clusters are heavily biased toward large, bright galaxies. We're missing most of the cluster members. The invisible universe includes the complete populations of galaxy clusters, all the small galaxies that we know should be there based on nearby examples, but that we can't detect at large distances. There's also the issue of galaxy evolution over cosmic time. Galaxies change. They merge with other galaxies. They form new stars. Old stars die. Gas flows in and out. The galaxies we see in the distant universe, seen as they were billions of years ago, look different from galaxies in the nearby universe. Early galaxies tend to be smaller, more irregular, and more actively forming stars. Modern galaxies tend to be larger, more organized into spirals or ellipticals, and forming stars at slower rates. This evolution is a key part of understanding cosmic history. But to really understand it, we need to observe large numbers of galaxies at different distances, corresponding to different cosmic epochs. We need thousands or millions of galaxies from each era to see the full range of properties and understand how they change over time. The problem is, we don't have that data for most of cosmic history. We have good samples of nearby galaxies and reasonable samples from a few specific epochs in the past where targeted surveys have focused. But there are huge gaps. For example, we have relatively few detailed observations of galaxies from the epoch 8 to 10 billion years ago, a crucial time when many galaxies were transitioning from active star formation to more quiescent states. The invisible universe includes all these unobserved galaxies at intermediate redshifts, galaxies that would fill in our understanding of how galaxies evolve, but that remain unseen because we haven't conducted deep enough surveys at those specific distances. Let's discuss the Milky Way's zone of avoidance in more detail. Our own galaxy is a disk of stars, gas, and dust, about 100,000 light-years across and only about 1,000 light-years thick in most places. We're located within this disk, about 26,000 light-years from the center. When we look toward the galactic center, or along the plane of the disk, we're looking through enormous amounts of dust. This dust absorbs and scatters light, particularly blue and ultraviolet light. It's like trying to see through a thick fog. You can't see far, and everything looks dimmer and redder than it actually is. This creates a zone of avoidance, a band around the sky where we can't see distant galaxies at optical wavelengths. The zone is roughly 20 degrees wide, centered on the galactic plane. That might not sound like much, but it covers about 10% of the entire sky. Within this zone are an estimated 100 million to several hundred million galaxies that we can't observe optically. We can detect some of them at infrared or radio wavelengths, because those wavelengths penetrate dust better than visible light. But infrared and radio surveys don't have the same depth and resolution as optical surveys. So most of these galaxies remain poorly studied or completely invisible. This has practical consequences. There might be large galaxy clusters hidden behind the Milky Way. There might be nearby galaxies we don't know about. In fact, astronomers have discovered several relatively nearby galaxies hidden in the zone of avoidance using radio and infrared observations. In 1994, they discovered the Dwingaloo 1 galaxy, a spiral galaxy, only 10 million light-years away. That's closer than many well-known galaxies. It had been hidden by Milky Way dust for decades. If we're still finding galaxies this close, hidden by our own galaxy, imagine what we're missing at greater distances. The invisible universe includes everything behind the zone of avoidance. It's not invisible in principle. It's invisible because we're looking from inside a dusty galaxy. From a vantage point outside the Milky Way, these galaxies would be perfectly visible. But we're stuck inside, and until we can send telescopes to locations far from the galactic plane or develop better techniques for seeing through dust, this portion of the universe remains hidden. Now let's talk about quasars and how they relate to the invisible universe. Quasars are extremely luminous objects powered by supermassive black holes at the centers of galaxies. Gas falling into the black hole heats up and emits enormous amounts of light, sometimes outshining the entire galaxy. Quasars were discovered in the 1960s, and for a while, they were mysterious. Astronomers didn't know what they were or why they were so bright. Today we understand that quasars are a phase in galaxy evolution. When a galaxy has plenty of gas available to feed its central black hole, it becomes a quasar. When the gas runs out, The quasar fades, and you're left with a normal galaxy containing a dormant supermassive black hole. Quasars are interesting for studying the invisible universe because they're so bright. We can detect quasars at enormous distances, farther than we can detect normal galaxies. The most distant quasars we've found are from when the universe was less than 1 billion years old, over 13 billion years ago. These quasars tell us that supermassive black holes, millions or billions of times the mass of the Sun, existed very early in cosmic history. That's surprising because we don't fully understand how black holes can grow so large so quickly. But here's the thing. For every quasar we detect, there are probably hundreds or thousands of normal galaxies at the same distance that we can't see because they're not bright enough. The quasar is like a lighthouse, brilliant and easy to spot, while the normal galaxies are like small boats with dim lanterns, nearly invisible against the dark ocean. So quasars give us a biased view of the early universe. We see the most extreme, most active galaxies because they're bright enough to detect. But we're missing the bulk of the galaxy population, the normal galaxies going about their business without actively feeding a central black hole. The invisible universe at high redshift is dominated by these normal galaxies. We know they must be there because we see their descendants in the nearby universe. But directly detecting them is incredibly difficult. Webb is helping, finding some of these normal high redshift galaxies, but even Webb can only scratch the surface. Let me tell you about gravitational lensing and how it helps us see parts of the invisible universe. Gravitational lensing occurs when a massive object, like a galaxy cluster, bends the path of light from a more distant object. It's a consequence of general relativity. Mass warps spacetime, and light follows that warped spacetime. If a massive cluster sits between us and a distant galaxy, the cluster's gravity can bend the light from that galaxy, magnifying it and making it appear brighter and larger than it would otherwise. In some cases, the lensing creates multiple images of the same galaxy or stretches it into long arcs. Astronomers use gravitational lensing as a natural telescope. By studying lensed galaxies, they can see objects that would be too faint to detect otherwise. The magnification can make a galaxy appear 10 or even 100 times brighter, bringing it within reach of our telescopes. This technique has revealed some of the faintest, most distant galaxies ever observed. Without lensing, these galaxies would be part of the invisible universe. Lensing pulls them out of obscurity and makes them visible. But lensing is rare. You need a massive cluster in just the right position between you and a background galaxy. Most distant galaxies aren't lensed. They remain invisible. Astronomers are conducting surveys to find as many lensed galaxies as possible, scanning the sky around known massive clusters. Projects like the Hubble Frontier Fields program observed 6 massive galaxy clusters in extreme detail, looking for lensed background galaxies. They found hundreds of them, revealing populations of faint galaxies that would otherwise be undetectable. But this is still a tiny fraction of the total. For every lensed galaxy we find, there are thousands of unlensed galaxies at similar distances that we can't see. They're part of the invisible universe, waiting for future technology or fortunate lensing configurations to bring them into view. Let's talk about the cosmic microwave background and what it tells us about the invisible universe. The cosmic microwave background, or CMB, is the oldest light in the universe. It's radiation left over from about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this recombination, the universe was opaque. Photons couldn't travel far without scattering off free electrons. After recombination, the photons were free to travel unimpeded. Those photons have been traveling through space ever since, and we detect them today as the CMB, a faint microwave glow coming from all directions. The CMB shows us what the universe looked like before any galaxies existed. It's a snapshot of the infant universe, and it's remarkably smooth. The temperature variations across the sky are only about 1 part in 100,000. This tells us the early universe was nearly uniform, with only tiny density fluctuations. Those tiny fluctuations were the seeds that grew into galaxies and galaxy clusters under the influence of gravity. But here's the key point. We can map the CMB with exquisite precision. Satellites like the Planck mission have measured the temperature of the CMB across the entire sky with incredible accuracy. This gives us information about the entire observable universe at that early epoch. In contrast, our maps of galaxies cover only a tiny fraction of the sky and only include the brightest object. So in a sense, the CMB is one of the few things in the universe we've observed completely. We've mapped the whole sky in microwave light. But that's the universe at 380,000 years old. The universe today, 13.8 billion years old, is vastly more complex and structured. All the galaxies, clusters, filaments, and voids developed from those tiny CMB fluctuations. But we haven't observed most of that structure. The invisible universe is everything that grew from those seeds, but that we haven't mapped yet. It's the difference between seeing a field of tiny seedlings and seeing the mature forest that grows from them. We've seen the seedlings in the CMB. We're still working on mapping the forest. Let me discuss cosmic noon, an era when the universe was about 3 to 6 billion years old. This was the peak of star formation in the universe. Galaxies were forming stars at their highest rates. If you could visit the universe during cosmic noon, you'd see vibrant, active galaxies everywhere, filled with young stars, supernova explosions, and swirling gas. Our local universe is relatively quiet. Most large galaxies, like the Milky Way, form stars slowly, processing only a few solar masses of gas into stars each year. But at cosmic noon, many galaxies were forming hundreds or thousands of solar masses worth of stars annually. The sky would have been brighter, more colorful, more energetic. Massive stars which live fast and die young would have been far more common. The rate of supernova explosions would have been dramatically higher. Studying cosmic noon is crucial for understanding where today's galaxies came from. Most of the stars in the Milky Way were formed during this era, when our galaxy was younger and more active. To understand our own origins, we need to understand what galaxies were like during this peak period. But observing galaxies from cosmic noon is challenging. They're 7 to 10 billion light-years away, far enough to appear faint. We have catalogues from surveys like Candel's that used Hubble to study specific fields in detail. But these surveys cover tiny areas of sky. We've observed thousands of galaxies from cosmic noon, maybe tens of thousands. There should be hundreds of billions from this era across the entire observable universe. We're seeing a tiny sample, the biggest and brightest. The normal and dwarf galaxies from this crucial epoch remained largely invisible. Galaxies that would tell us about the full range of star formation and evolution during the universe's most active period. What's particularly interesting is that cosmic noon galaxies looked very different from modern ones. They were often irregular in shape, lacking the organized spiral or elliptical structures we see today. They were clumpier, with star formation concentrated in dense knots throughout the galaxy rather than in smooth disks or arms. They had higher gas fractions, meaning a larger percentage of their mass was in gas rather than stars. This makes sense because they were actively converting gas into stars at high rates. Understanding how these messy, active, cosmic noon galaxies transformed into the organized, quieter galaxies we see today is one of the major questions in galaxy evolution. The transformation involves complex processes like gas consumption, feedback from supernovae and black holes, and galaxy mergers. But we can't fully understand these processes without observing large samples of galaxies throughout the transition period. Let's explore galaxy mergers in more detail. Galaxies don't exist in isolation. They interact gravitationally. Sometimes they collide and merge. When two galaxies merge, their stars, gas, and dust mix together over hundreds of millions of years. The merger can trigger intense star formation as gas clouds collide and compress. It can funnel gas toward the central black holes, potentially triggering quasar activity. And it can completely transform galaxy structures. Two spiral galaxies merging might produce an elliptical galaxy. The orderly rotation of the spirals gets disrupted by the gravitational chaos of the merger, scrambling the stars into a more spherical distribution. A small galaxy merging into a larger one might be completely torn apart. Its stars scattered throughout the larger galaxy, like sugar dissolving in coffee. Mergers are a key process in galaxy evolution. Galaxies grow by consuming smaller neighbors, gradually building up mass over billions of years. The Milky Way has evidence of past mergers written into its structure. Streams of stars in our halo, the diffuse region surrounding the disk, are the remnants of dwarf galaxies that merged with the Milky Way billions of years ago. These stellar streams have different chemical compositions and orbital patterns than stars formed in the Milky Way itself, marking them as immigrants from other galaxies. We're witnessing active mergers right now. The antennae galaxies, about 65 million light-years away, are two spiral galaxies in the process of colliding. Long tidal tails of stars stream away from the collision site, pulled out by gravity. Bright knots of star formation mark regions where gas clouds have collided. In a few 100 million years, these two galaxies will complete their merger and become a single elliptical galaxy. The mice galaxies, about 300 million light-years away, are another famous example. They're named for their long tails that resemble mouse tails. These tails are made of stars, flung out during the gravitational interaction. Eventually, these stars will fall back and be incorporated into the merged galaxy. Closer to home, the Andromeda Galaxy is heading toward the Milky Way at about 110 kilometers or 68 miles per second. In about 4 to 5 billion years, the two galaxies will collide. Simulations show that the merger will be spectacular, with multiple close passes before the galaxies finally settle into a single elliptical galaxy. Our solar system will likely survive intact, flung into a different orbit, but not destroyed. The night sky during the merger will be dramatically different, with Andromeda looming large and bright, growing bigger over millions of years until it dominates the sky. But detecting mergers at large distances is difficult. The disturbances in galaxy structure are subtle and require high-resolution images. At distances of billions of light-years, most mergers remain invisible. We can see the end products, large elliptical galaxies that likely formed from mergers, but we can't observe the mergers themselves in their early stages. Now, let's discuss the role of computer simulations in understanding the invisible universe. Since we can't observe most galaxies directly, astronomers use computer simulations to model what the invisible universe should look like. These simulations start with the tiny density fluctuations observed in the cosmic microwave background. They apply the laws of gravity gas dynamics, and star formation to evolve those fluctuations forward in time. The simulations create virtual universes where galaxies form, merge, and evolve over billions of years. Modern simulations can track billions of particles representing dark matter, gas, and stars. They can reproduce many of the observed properties of galaxies, including their sizes, shapes, and distributions. Projects like Illustris, Eagle, and TNG have created remarkably realistic virtual universes. When you look at the output from these simulations, you see a cosmic web of galaxies very similar to what we observe in the real universe. The simulations predict that there should be about 2 trillion galaxies in the observable universe, matching the observed estimate. They predict populations of dwarf galaxies, low surface brightness galaxies, and other objects that we see in limited numbers in reality. These simulations are our best guide to the invisible universe. They tell us what should be out there even if we haven't seen it yet. When a simulation predicts millions of ultra-faint dwarf galaxies, and we've only found a few dozen, we can infer that the rest are part of the invisible universe, too faint for current telescopes, but present in reality just as they are in the simulations. The simulations have limitations, of course. They're based on our current understanding of physics, which might be incomplete. They use approximations and simplifications because we can't model every detail. But they're powerful tools for extending our knowledge beyond what we can directly observe. Let me tell you about the future of galaxy surveys and how they'll reduce the size of the invisible universe. As I mentioned, the Nancy Grace Roman Space Telescope will launch in the late 2020s. Roman's wide field of view will allow it to survey large areas of sky quickly. Its infrared sensitivity will enable it to detect faint, distant galaxies. Roman's mission includes a high-latitude wide area survey that will cover thousands of square degrees of sky, observing hundreds of millions of galaxies. This will be a major step forward. Instead of mapping tiny pencil beams through the universe, Roman will map large volumes, giving us a much better sense of cosmic structure and galaxy populations. On the ground, the Vera C. Rubin Observatory is conducting the Legacy Survey of Space and Time, or LSST. Rubin Observatory has an 8.4-meter, or about 28-foot telescope with an enormous field of view. It will photograph the entire visible sky every few nights, creating a movie of the changing universe. Over its 10-year mission, LSST will catalog billions of galaxies, asteroids, supernovae, and other objects. The data will be a treasure trove for astronomers. LSST won't go as deep as Hubble or Webb, but it will cover far more sky. It's a different approach, breadth versus depth, and it's complementary to deep pencil beam surveys. The extremely large telescope, being built by the European Southern Observatory in Chile, will have a 39-meter or 128-foot primary mirror. It will be the largest optical telescope ever built. ELT will be able to study individual stars in distant galaxies, observe the atmospheres of exoplanets, and probe the early universe in unprecedented detail. It won't survey large areas like Roman or LSST, but it will provide exquisite detail on specific targets. ELT will help us understand the galaxies we've found in greater depth, characterizing their structures, stellar populations, and chemical compositions. The Square Kilometre Array, a next-generation radio telescope being built in Australia and South Africa, will be the most sensitive radio telescope ever constructed. SKA will survey the sky at radio wavelengths, detecting neutral hydrogen gas in galaxies. Hydrogen is the most abundant element in the universe, and it emits a characteristic radio signal at 21 centimeters or about 8 inches wavelength. By mapping hydrogen, SKA will trace the distribution of gas in galaxies, study galaxy rotation curves, and detect galaxies that might be too faint to see at optical wavelengths, but that contain lots of gas. SKA will add another dimension to our maps of the universe, revealing the invisible reservoirs of gas from which future stars will form. All these projects will help, but they won't eliminate the invisible universe. Even with all these telescopes working together, we'll still observe only a small fraction of the 2 trillion galaxies. We might go from 0.0025% to 1 or 2%. That's progress. But 98 or 99% will still be invisible. The fundamental problem is time. There are only so many hours in a day, so many nights in a year, so many years in a human lifetime or a mission lifetime. We can't observe everything. We have to make choices, and every choice means some part of the universe remains unseen. Let's think about the philosophical implications of the invisible universe. What does it mean to live in a universe where most of what exists is beyond our ability to observe? Does the invisible universe exist in the same way the observed universe does? Philosophers have debated questions like this for centuries. If a tree falls in a forest and no one hears it, does it make a sound? If a galaxy exists but no one observes it, is it real? From a scientific perspective, the answer is clearly yes. The galaxies we haven't observed are just as real as the ones we have observed. They're made of the same matter, governed by the same laws of physics. The light from invisible galaxies is traveling through space right now. It exists. It's just that we haven't captured it yet. There's nothing mystical or uncertain about the invisible universe. It's invisible only in the sense that we haven't looked yet, not in the sense that it's fundamentally unknowable or exists in some ambiguous state. But there's still something humbling about it. We're finite beings with finite resources, trying to understand an effectively infinite universe. We'll never see everything. We'll never know everything. There will always be galaxies we haven't observed, stars we haven't studied, planets we haven't discovered. The invisible universe is a permanent reminder of the limits of human knowledge. No matter how far we push our technology, no matter how many telescopes we build, most of the universe will remain unseen. At the same time, there's something inspiring about it. The invisible universe is an endless frontier. There's always more to discover. Every observation has the potential to reveal something new and surprising. The universe is far more interesting than we imagined, and the invisible portions likely contain wonders we can't even conceive of yet. This keeps science exciting. We're not filling in the last few details of a nearly complete picture. We're still in the early stages of mapping the cosmos. The invisible universe ensures that future generations will have just as much to explore as we do. Let me bring this back to the human scale for a moment. Why should you care about the invisible universe? You're not an astronomer. You're not building telescopes or analyzing data. What does it matter that we've only observed a tiny fraction of galaxies? I think it matters because it changes your perspective. We live in an age where information seems abundant. The internet contains vast libraries of human knowledge. We can find answers to almost any question with a quick search. It's easy to feel like we know a lot, like we've figured most things out. The invisible universe reminds us that we haven't. Not even close. The universe is vastly larger and more complex than our everyday experience suggests. Most of what exists is beyond our current ability to study. This should inspire a sense of wonder and humility. Wonder at the sheer scale and richness of the cosmos. humility at how little we actually know despite all our progress. When you look up at the night sky, you're seeing a tiny fraction of what's out there. The invisible universe surrounds you in all directions, vast beyond comprehension. That's worth thinking about sometimes. It also has practical implications for how we think about life in the universe. If we've only observed 0.0025% of galaxies, we've barely begun to search for signs of life. Every galaxy contains billions of stars. Every star might have planets. The number of potentially habitable worlds in the universe is staggering. If life is even moderately common, the universe should be teeming with it. But we've looked at such a tiny fraction of the sky that our failure to find signs of life so far doesn't mean much. The invisible universe almost certainly contains life, perhaps even intelligent technological civilizations. We just haven't found them yet because we haven't looked in enough places. This should make us more optimistic about the search for extraterrestrial intelligence. We're not running out of places to look, we're just getting started. The invisible universe contains trillions of galaxies we haven't examined. Each could host billions of habitable worlds. The odds that we're alone seem vanishingly small when you think about the scale involved. It's not a question of whether life exists elsewhere. It's a question of when and how we'll find it. Let me conclude by bringing together everything we've discussed. The observable universe is roughly 93 billion light-years across and contains approximately 2 trillion galaxies. These galaxies range from dwarf galaxies with a few million stars to giant ellipticals with several trillion stars. Each galaxy is a city of stars, a gravitationally bound system that has existed for billions of years. The total number of stars in the observable universe is estimated at around 200 billion trillion, a number so large it's meaningless to human intuition. But we've only observed a tiny fraction of this cosmic census. As of 2025, the most comprehensive galaxy surveys have catalogued between 10 million and 50 million galaxies in various levels of detail. That's roughly 0.0025% of the total. For every galaxy we've observed, there are about 40,000 galaxies we haven't looked at. Most of these invisible galaxies are small, faint, distant, or obscured by dust. They're not invisible in principle. They're just invisible because we haven't pointed our telescopes in the right direction or looked deep enough or waited long enough. The invisible universe includes dwarf galaxies too faint to detect at cosmological distances, low surface brightness galaxies spread too thin to stand out against the sky, galaxies hidden in the zone of avoidance behind Milky Way dust, early galaxies from cosmic dawn that are too distant and faint for current instruments, normal galaxies at cosmic noon that are outshone by their quasar neighbors, merging galaxies whose disturbances are too subtle to resolve, and intra-cluster stars drifting between galaxies in clusters. It includes everything in regions of sky we haven't surveyed, and everything below the detection limits of our telescopes. The invisible universe is the majority of what exists. The vast cosmic population we know must be there but haven't seen yet. We're making progress. Every year, new telescopes come online and new surveys catalogue more galaxies. The James Webb Space Telescope is revealing the early universe in unprecedented detail. The Euclid mission is mapping billions of galaxies across large areas of sky. Future missions like the Roman Space Telescope, the Extremely Large Telescope, and the Square Kilometre Array will push the boundaries even further. We'll go from having observed 0.0025% of galaxies to perhaps 1% or even a few percent over the next few decades. But even at a few percent, more than 95% of the universe will remain invisible. The task is simply too large. There are too many galaxies and not enough telescope time to observe them all. This doesn't mean we should give up. Every galaxy we observe adds to our understanding. We learn about galaxy formation and evolution, about dark matter and dark energy, about the history and structure of the universe. We don't need to observe every galaxy to understand the universe. A well-chosen sample can tell us a lot, but we should remain humble about the limits of our knowledge. Most of the universe remains unexplored. Most of cosmic history remains unwitnessed. The invisible universe is vast, and it will remain largely invisible for the foreseeable future. So the next time you look up at the stars, remember this: you're seeing a few thousand points of light, a tiny fraction of the 100 billion or more stars in our galaxy. Beyond our galaxy are 2 trillion other galaxies, each containing billions of stars. We've observed in detail fewer than 50 million of those 2 trillion galaxies. The rest are invisible, not because they can't be seen, but because we haven't looked yet. They're out there right now, shining in the darkness, waiting to be discovered. The invisible universe surrounds us, vast beyond comprehension. A reminder that the cosmos is far larger and more mysterious than anything we can fully know. Let me tell you about some specific observation challenges that contribute to the invisible universe, because understanding the technical barriers helps explain why so much remains unseen. When astronomers observe the sky, they're fighting against numerous sources of noise and interference. There's light pollution from cities, which brightens the sky and makes faint objects harder to see. There's atmospheric turbulence, which blurs images and reduces resolution. There's the moon, which when bright can wash out faint objects. There's even dust and gas in our solar system, zodiacal light and scattered sunlight that creates a faint glow across the sky. All of these factors limit what we can detect. Even in space, above Earth's atmosphere, there are challenges. Cosmic rays, high-energy particles from space constantly bombard detectors, creating false signals that must be filtered out. The instruments themselves generate noise. Detectors have a dark current, a small signal, even when no light is hitting them. Electronics produce thermal noise. Every photon we're trying to detect from a distant galaxy must be distinguished from all these sources of noise. For very faint objects, the signal might be only slightly larger than the noise. You need long integration times, exposing the detector for hours or days to build up enough signal to reliably detect the object. This is why deep surveys take so long. The Hubble Ultra Deep Field required over 11 days of total exposure time spread across hundreds of orbits. Hubble would point at the same patch of sky for about an hour during each orbit, then move away to do other observations, then come back and point at the same patch again. After hundreds of these exposures were combined, the resulting image revealed galaxies so faint that they were only a few photons above the background noise. This painstaking process can't be rushed. You can't observe a galaxy that faint in a few minutes. You need to collect photons patiently, one by one, until you have enough to create an image. Now, multiply this by the entire sky. To observe the whole sky to the depth of the Hubble Ultra Deep Field would require about 10 million similar observations. If each one takes 11 days, you're looking at over 100 million days of telescope time. That's about 300,000 years. Obviously, we can't dedicate a telescope to a single project for 300,000 years. Even if we built hundreds of Hubble-class telescopes and ran them all simultaneously, it would take thousands of years. This is the fundamental barrier. The invisible universe is invisible largely because we don't have time to look at it all. There's also the challenge of identifying what you're seeing. When you take a deep image of the sky, you might capture thousands or tens of thousands of faint objects in a single field. Most of these are galaxies, but some are stars in our own galaxy, some are asteroids in our solar system, some are artifacts or noise. You need to distinguish between these. Galaxies typically appear as extended fuzzy blobs, while stars appear as point sources. But very distant galaxies can also appear as point sources if they're too far away to resolve their structure. You need multiple observations at different times to identify asteroids, which move against the background stars and galaxies. You need spectroscopy to confirm that an object really is a distant galaxy and not a nearby star that happens to have colors similar to a high redshift galaxy. All of this takes time and effort. For every object detected in a deep image, hours of analysis might be required to classify it properly. Even with automated algorithms and machine learning, there's a limit to how fast this can be done. The invisible universe includes not just objects we haven't photographed, but also objects we've photographed but haven't properly identified or classified yet. There are probably millions of galaxies sitting in existing telescope data archives that haven't been thoroughly analyzed because there simply aren't enough astronomers to go through all the data. Let me talk about the concept of selection effects and how they bias our view of the universe. Every survey has selection effects, systematic biases that make some types of objects easier to find than others. Bright objects are easier to find than faint ones, so surveys are biased toward bright galaxies. Large objects are easier to resolve than small ones, so surveys are biased toward large galaxies. Objects with certain colors stand out more than others, creating color biases. Objects in certain regions of sky might be preferentially observed because they're visible from particular observatories or because they happen to be in fields that were targeted for other reasons. All these selection effects mean that the galaxies we've observed are not a representative sample of all galaxies. They're a biased sample skewed toward bright, large, colorful galaxies in well-studied regions of sky. When we try to understand galaxy populations based on our observations, we have to account for these biases. We have to ask, what fraction of the total population are we actually seeing? For some types of galaxies, like giant bright ellipticals, we might be seeing a large fraction, maybe 50% or more of those that exist in surveyed regions. For other types, like ultra-faint dwarfs or low-surface brightness galaxies, we might be seeing less than 1%. The invisible universe is disproportionately made up of the types of galaxies our surveys are bad at finding. Astronomers try to correct for selection effects using statistical methods. They model the selection function of a survey, the probability of detecting an object as a function of its properties. Then they can estimate the total population by accounting for what the survey would have missed. This is how we arrive at estimates like 2 trillion galaxies, even though we've only observed 50 million. The estimate is based on observations of the galaxies we can see, plus statistical corrections for the galaxies we know we're missing. But these statistical corrections have uncertainties. The true number might be 1.5 trillion or 3 trillion. We won't know for sure until we observe a much larger fraction of the universe. Now let's think about the timescales involved in cosmic evolution and how they relate to the invisible universe. Galaxies evolve slowly. A typical galaxy might form over hundreds of millions of years, gradually gathering gas and dark matter, forming stars, and growing in mass. Once formed, it evolves over billions of years, sometimes forming stars continuously, sometimes experiencing bursts of star formation triggered by mergers or gas inflows. sometimes becoming quiescent, with very little ongoing star formation. These are long timescales, far longer than a human lifetime, far longer than all of human civilization. We can't watch a galaxy evolve in real time. We can only see snapshots. But by observing many galaxies at different distances, corresponding to different cosmic times, we can piece together an evolutionary sequence. We see what galaxies looked like 1 billion years after the Big Bang by looking at galaxies that are so far away their light has been traveling for 12.8 billion years. We see what they look like at 5 billion years by looking at galaxies at intermediate distances. We see what they look like today at 13.8 billion years by looking at nearby galaxies. By combining these snapshots, we construct a picture of how galaxies evolve over cosmic time. But this only works if we have good samples of galaxies at all different distances. Gaps in our observations create gaps in our understanding of evolution. The invisible universe creates these gaps. There are epochs in cosmic history where we have relatively few galaxy observations, either because galaxies at those redshifts are particularly hard to detect, or because surveys haven't focused on those distances. These gaps leave uncertainties in our evolutionary models. We might see that galaxies at redshift 2 look a certain way, and galaxies at redshift 0.5 look another way, but without observations at intermediate redshifts, we don't know exactly how or when the transition occurred. The invisible universe obscures the details of cosmic evolution. Let me discuss one more aspect of the invisible universe that's particularly fascinating. The universe might contain entirely unexpected structures or phenomena that we haven't discovered yet because we haven't observed enough of it. History shows that whenever we've pushed into new observational territory, whether it's looking at new wavelengths, achieving higher resolution, or reaching greater distances, we've found surprises. Quasars were a surprise when first discovered. Gamma-ray bursts were a surprise. Dark matter was a surprise. Dark energy was a surprise. The large-scale structure of the cosmic web was a surprise. Each of these discoveries required observations that pushed beyond what was previously possible. What surprises might be hiding in the invisible universe? We don't know, obviously. That's what makes them surprises. But it's reasonable to expect that when we finally observe a significant fraction of the 2 trillion galaxies, we'll find phenomena we didn't anticipate. Maybe there are types of galaxies with properties unlike anything we've seen. Maybe there are structures on scales larger than we thought possible. Maybe there are populations of objects we haven't imagined yet. The invisible universe is a reservoir of potential discoveries, and we won't know what's there until we look. This is why it's important to continue pushing the frontiers of observation even when we don't have a specific prediction to test. Exploratory surveys that map large volumes of the universe without targeting specific objects often yield the most surprising discoveries. The Sloan Digital Sky Survey wasn't designed to find any particular type of object. It was designed to map the sky systematically and see what was there. It discovered quasars at redshifts higher than had been seen before. It revealed the detailed structure of the cosmic web. It found unusual galaxies that didn't fit existing categories. These discoveries came from simply looking, from making the invisible universe visible. The same will be true in the future. When the Roman Space Telescope surveys billions of galaxies, it will undoubtedly find unexpected things. When the extremely large telescope studies distant galaxies in unprecedented detail, it will reveal phenomena we haven't seen before. The invisible universe is not just more of the same. It contains unknowns, and unknowns are what drive science forward. So what have we learned tonight? We've learned that the observable universe contains about 2 trillion galaxies, but we've only observed in detail a tiny fraction of them. We've learned about the different types of objects that make up the invisible universe, from dwarf galaxies and low-surface brightness galaxies to distant primordial galaxies and intergalactic stars. We've learned about the challenges of observation, the time and resources required to detect faint, distant objects. We've learned about selection effects and how they bias our view of the universe. And we've thought about the philosophical and practical implications of living in a universe where most of what exists remains unseen. The invisible universe is vast, far larger than the observed universe. For every galaxy we've studied, there are tens of thousands we haven't. For every star we've catalogued, there are trillions we haven't. For every planet we've detected, there are countless others waiting to be found. This should fill us with a sense of wonder and humility. Wonder at the sheer scale and richness of the cosmos. Humility at the limits of our knowledge, despite all our technological progress. But it should also inspire us to keep exploring. The invisible universe is not forever invisible. It's simply unseen so far. With better telescopes, more observing time, improved analysis techniques, and continued dedication, we can make more of it visible. We'll never see it all. That's probably impossible given the constraints of time and resources, but we can see more. We can push the boundaries further. We can reveal new corners of the cosmos and discover new wonders. And that's worth doing, not just for the scientific knowledge we gain, but for the broader perspective it gives us on our place in the universe. Thank you for joining me on this journey through the invisible universe. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep dives into the cosmos. Remember, the universe is far larger than what we can see. Every time we look, we find something new. And that's the beauty of it. The invisible universe isn't empty. It's full of wonders we haven't discovered yet. It's full of galaxies waiting to be catalogued, stars waiting to be studied, and perhaps even civilizations waiting to be contacted. The frontier of cosmic exploration stretches endlessly before us. We're surrounded by mysteries, and that makes this the most exciting time to be alive and looking up at the stars. Good night, and may you never look at the night sky the same way again.